What is the gas fee? In the blockchain world, the gas fee is a fee that users have to pay to the blockchain network for each transaction. For example, when a user makes a transfer on Ethereum, miners must package his transaction and put it on the blockchain to complete the transaction. This process consumes the computing resources of the blockchain, and the fee paid to miners is called the gas fee. Imagine that each public chain is a society or a city, and gas would be the currency that users need for various activities in the city, and the economic designs of gas have far-reaching impacts on the public chain's future development. Today, we will illustrate the significance of the gas economy from the perspectives of performance and value capture. In early May, Solana's mainnet lost consensus, and block generation was suspended for 7 hours. The mainnet was down due to the NFT minting of a new NFT project. Users turned to bots for sending transactions as much as possible to increase their success rate of minting. This led to 6 million transactions per second on the Solana mainnet, which jammed the network. Moreover, as Solana transmits consensus messages as a special transaction message between validators, the heavily congested network also disabled the normal transmission of consensus messages, eventually leading to the loss of consensus. This is not the first downtime of Solana. Last September, the public chain suffered a 17-hour downtime due to the massive trading volume created by on-chain bots during the launch of the hit project Raydium. A 30-hour Solana downtime incident happened at the end of January 2022 when the BTC price plunged from $44,000 to $33,000 during a market crash and created plenty of arbitrage opportunities. Meanwhile, the liquidation/arbitrage bots on Solana, which center on DeFi, kept creating massive transactions, which resulted in network downtime. When comparing Solana to a conventional IT system, we can tell that the downtime resembles a DDoS attack. A DDoS, distributed denial of service, attack refers to adding traffic from multiple sources to exceed the processing capacity of a network so that real users would not be able to acquire them. Attackers often launch a DDoS attack by sending more traffic to a network than it can handle or sending more requests to an application than it can manage. Instinctively, many people would think that Solana's downtime is rooted in its public chain designs, the monolithic design of Solana and Airtable. At the moment, mainstream public chains use two kinds of designs, the modular and the monolithic. The modular architecture refers to a modularized deployment where consensus, storage, and execution are implemented separately so that the collapse of the execution layer will not compromise the security of the consensus layer. At the same time, mainstream designs adopted by Avalanche's Subnet, ETH2.0, and Celestia's Rollup can all diverge massive transactions. On the other hand, although Solana as a whole is designed to enable fast transactions, scalability and security were sacrificed. However, the modular design of a public chain is not the key because although the consensus stayed secure, the individual rollup could still suffer from downtime when facing overwhelming transactions in a very short period. In other words, the modular design just lowered the systemic risks, e.g., a certain rollup could halt but the rest can survive, for the public chain. The gas design is the real reason behind Solana's downtime, and more network downtime is on the way if the design is not improved. The figure below shows the gas designs of 3 mainstream public chains.